Good morning, folks. So we are going to begin working on chapter 19. Traditionally, this would have been our last chapter, but this is one that we definitely wanted to get to and cover the topics of. So we're going to get through 19, and then with whatever time we might have left after this chapter, we're going to kind of reverse back to chapter 11. But we're definitely going to want to hit some major foundations for calculus next year, because many of you are going to be entering that course. So chapter 19 deals with limits of functions. So limits of functions and limits of sequences are similar in their intuitive definition. They basically are defining a behavior or a trend that something approaches. However, limits of functions have two very key differences. The first is with a sequence, the variable n is only going to be integers because we're talking about a place or a term in the sequence, which is only an integer value. Whereas for functions, the variable can take on any real number. We can plug in fractions, decimals, irrational numbers. So we're going to begin to see x being any value rather than just the integers. Excuse me. And then the other big difference is with limit sequences, we're always seeing what happens as n increases without bound, right? N is going toward infinity. With limits of functions, we can approach any real number. It doesn't necessarily what's happening as x gets very large. It can be, but it could also be what's happening as x approaches a particular number, a single value. And that's kind of what we're going to start with. So I see the definition's right in front of you. I tried color coding some of the pieces of the definition to the notation. So basically a limit is a value of a function that the function gets close to as x approaches a certain value. So the input is getting really, really close to a particular number. Then what is the function getting really, really close to as an output value? That's what limits of functions are describing. So the notation is going to be right here we see on the bottom, very similar to what we saw for sequences, but instead of taking the limit of a sequence, it's now a function. And x can approach any real number in the domain of f, in the domain of f of x, okay? So x is getting really, really close to some input value, and if f of x, as that happens, is getting really, really close to some output value, then we define that the value it's getting close to is the limit. So let's kind of see a couple of examples here. Um, I'm trying not to scroll too far down here. So I have the function x squared minus 4 over x minus 2. Now, obviously that has a domain restriction in 2, but we might still see a particular pattern or trend as we approach 2. So I'm going to ask, what is the limit of that function x squared minus 4 over x minus 2 as x approaches 2? And I already set up handy dandy Desmos here. So we're going to tackle this as a graphing problem. So I turned on my graph. Obviously, it does look very linear. So it almost looks like we can just say, oh, look, there's 2. Where's my answer? But we're going to kind of hit on the definition here. So I made a table of values, okay? So if x is 1, which is pretty darn close to 2, right? We're seeing that the output is 3. Well, what about 1.5? Well, it's 3.5. 1.9. You're starting to see as the x values get closer and closer to 2, what's happening to the f of x values. Now, keep in mind, I can't plug 2 in. If I plug 2, it's undefined. So that's not really helpful to always just plug an x value in and get the answer out. You really have to figure out what's happening as we get near the x coordinate. And it's only going to exist if both sides of the value, both sides of 2 are doing the same thing. So everything we see on the graph right now, all those black ordered pairs that are on the graph of f, those are all to the left of positive 2. Okay, so if I'm looking at what's going on at 2, all of these are smaller values. So it would help if we plug in a couple values a little bit larger than the x coordinate we're looking at and seeing what happens as we get closer to the x coordinate from the right side. So 3 is to the right. Okay, well, 2.5 is to the right. 2.1 is to the right. 2.01. And you can kind of see that both directions, as I get closer and closer to x equals 2, f of x is getting closer and closer to a value of 4. And that's exactly what we would say the limit is. So the limit, I'm going to go back to my worksheet, make sure I have the right one. The limit as x approaches 2 of x squared minus 4 over x minus 2 is 4. And we saw that because we have the values on the left side and the right side both agreeing that the direction from the left and the direction from the right both hit 4. Okay, let's see a little bit more definition, kind of background information. So I mentioned this briefly already in explaining the example, but the limit exists if and only if the limit from the left and the limit from the right both equal the same value, meaning they converge to one another. So because the left side of 2 was approaching a value of 4 and the right side of 2 was approaching a value of 4, the limit was 4 because both of those agreed with one another as a value. Okay? The overall value is sometimes called a two-sided limit. If we're only talking about a left side or right side behavior, that's a one-sided limit. So here's some new notation. So we see this little, I don't want to call them exponents, we'll call them superscripts, right? So x approaches a with a little superscript of a negative symbol. That simply means we're approaching a on the left side. So before, those would be all the values that were less than 2 would be my left side limit, okay? And we would just say 2 with a little exponent of a negative symbol, okay? It's not actually an exponent, but it's just a marker saying I'm on the left side. And of course, the positive symbol in an exponent position, the positive superscript, that's the right side of 2. So those were all the values a little bit greater than 2, and we were approaching on the right side of 2. That would be the right side limit. Well, if those two one-sided limits equal each other at some number, that number is the overall limit, and we can write it as a function or as a limit of a function without any of those superscripts. Okay? So let's see another example. I'm going to take a look at something where we see something different happen. So I'm going to take the limit as I get close to 0 of the absolute value of x divided by x. So we're going to hide these, and we're going to bring up the graph of absolute value of x. So what we see here is obviously two very different things are happening on the positive values and the negative values, right? So let's put some numbers in just like we did before. So -1 gives me a -1, negative 0.1, negative 0.01, negative 0.00001. Everything to the left of 0 is going to give me a value of -1. Doesn't matter that it's not changing. It's still approaching a value of -1, if not equal to a value of -1 for everything to the left. So we say the left side limit is -1. And then we're going to go to the right. To the right, +1 gives me, obviously, +1 I get out. Positive 0.1, whoops, 0.1 gives me a +1. 0.01, 0.001, all of those values are going to give me a +1. So because that value is approaching a +1 to the right of 0, the right-hand limit is 1. Well, we have the right-hand limit equal 1, the left-hand limit equals -1. Those don't agree. which means the overall limit here does not exist, okay? Which we saw in sequences already. If the limit doesn't really hit a value, it does not exist. So let's see one last quick graphical example. Here is a graph. This is my function f of x, okay? So I'm going to ignore the a through f to the left side here because I'm going to try and keep this example pretty short. But I'm looking at the x coordinate 1, okay, right here. Well, the graph a little bit to the left looks like it's going to get closer and closer to this open circle. And a little bit to the right, it's getting closer and closer to this open circle. As the x coordinates are getting closer to 1, the graph is getting closer to that value of the open circle. So the limit as I approach x equals 1 is 3, the y coordinate of the circle. But notice the function's not defined at 3. The function is defined at 1 because of this little circle down here is actually, it's almost like I put one dot at there, but the rest of the graph was this downward negative slope line, okay? So limits and the value of the function might not always agree with one another, and that's okay. Now, we're going to spend another day trying to explain this because this is definitely a topic that is one of those things where it might take some people 2 seconds to grasp the concept, and that's awesome. Other people, you need to work through and you need to practice a lot of examples before it clicks and you really understand it. So we're definitely going to slow things down because this is such an important chapter for calculus next year that the more you can practice and work with it this year, the better you're going to be for the beginning of calculus next year. So take a look at some of the practice material on the course page, reach out with questions, and good luck.